This is number 68 in chapter 13, and it has two parts. In part A, it gives us two different rate constants that go along with two different temperatures. We have a rate constant of 0.000122 reciprocal seconds, and this was at 27 degrees Celsius. And then there's another rate constant, 0.228 reciprocal seconds, and this was measured at 77 degrees Celsius. And the question is asking us estimate our activation energy. So anytime we're looking at getting the activation energy, we have to use the Arrhenius equation. And so the Arrhenius equation would be the natural log of K2 over K1 is equal to our activation energy over R times 1 over T1 minus 1 over T2. Our R value is in joules per mole Kelvin, so that means our temperatures need to be in Kelvin as well. That means that this is 300 Kelvin, and our 77 would be 350 Kelvin. So we need those temperatures to be in Kelvin. This is pretty much a plug and chug. We have our temperatures, our Ks, we just want to solve for our activation energy. So to start the process, we have natural log of K2, so 0.228 over the other rate constant, 0.000122. We're taking the natural log of that. That's going to equal our activation energy, which is what we're looking for. Over our R constant, 8.314, and that's joules per mole Kelvin. And so that's why our temperatures must be in Kelvin as well. And we want to make sure that our temperature matches up with our equilibrium constant. So our K2 is 0.228. That means our T2 must be 350 Kelvin. So if we begin to start to solve for this, we would have the natural log of this fraction, which turns out to be 1868.852. And then that's going to equal our EA over R, 8.314, times the difference of these two fractions, which turns out to be 0.000476619. We do some rearranging, take the natural log of 1868, we get 7.533. We bring over our 8.314, and we bring over our 0.000476619. And that is going to equal our activation energy. And when we solve that, we get a value of 131,521 joules per mole, or roughly 132 kilojoules per mole, depending on if you're rounding. So that's part A, looking at calculating the activation energy, roughly 132 kilojoules per mole. Part B then is looking to solve for a rate constant at 17 degrees Celsius. So we're going to have to use the equation again. We're going to still have to use the natural log of our K2 over our K1 is equal to EA over R times 1 over T1 minus 1 over T2. Again, we have to have our temperatures in Kelvin, so this would be 290 Kelvin. And so we could pick any of the two rates from part A. I'm going to pick the larger of the two rates to solve this. So if we start to substitute, it would be the natural log of K2, and I'm going to use again the 0.228 And that's what we're trying to solve for, the K in the denominator, and that K would be the one that's done at 17 degrees Celsius. And that's going to equal our activation energy, and that's 131,521 joules over our R value, 8.314 joules per mole Kelvin, and that'd be 1 over T1, which is 290, minus 1 over T2, which was 350. So we go one more step. Still haven't done anything to the right of the expression. We start to divide these two. We get 15,819.2 times then 0.0005911. We go a little bit further, get rid of the natural log, so we just have our fraction on the left, and then that would be e to this product, which is 9.35125. If we then solve for our K at 17 degrees Celsius, that would be equal to 0.228 over e to the 9.35125. And so that's going to equal 0.228 over 11,513.22, which equals then our rate constant, 1.98 times 10 to the negative fifth. And that would be our rate constant for the reaction at 17 degrees Celsius, or 290 Kelvin.